Hello everyone, I'm Andrew. This is going to be a presentation on robots and reinforcement learning. How many here have done machine learning before? Anyway. Okay, some of you. Has anyone done reinforcement learning anyway? I know you have. Okay, cool. A little bit. So it's an emerging new field. The stuff that has come out in the last 5 years. There was a previous field, but they ran into a wall where they couldn't compute enough. So we waited a couple years, and now we're at a point where we have the computation power and we have the algorithms together. So it's real fun right now. So let's get started. That's me. So what is reinforcement learning? It's kind of this feedback loop between an environment and an agent, and that agent is your bot or your AI. And so what the environment will do is you start at some state, and you'll give it an action, and then you'll go to another state. And every time you take an action, there'll be some reward to that action. A good example is if you're playing Pong, you can move up and down, and if you get the ball past yourself, that's a -1. You have just lost a point. And if you get the ball into the other person's goal, that's a +1. So that would be your kind of reward. And your actions would be moving up and down. And your agent is just an object that can take in states such as pixels of a board and then output actions. Does that make sense? So we have agents, environments, states and actions, and rewards. So these are the main things that build up all of our algorithms. There's two major types of approaches to reinforcement learning problems. There's model-based reinforcement learning, and in that you have an environment and you want to try and model the environment. So I want to be able to look at a state and tell you what's my likely reward to get out of here. So say I'm looking at a state where I can see the Pong ball is behind my paddle. I'm going to tell you that that's going to be a -1 reward. I know I'm about to be penalized. So what a model-based approach would be is, how do I make sure that state doesn't happen, and how do I push myself towards states where I know that there's a positive reward? Policy-based models or agents do something different. They don't look at the environment to model it. They just try and take good actions. So their whole goal is, if I take an action and I win more, I'm going to keep taking that action. If I take an action and I lose, I'm going to stop taking that action as much. That makes sense to everyone? We're going to go over it more. So applications of reinforcement learning, these are kind of exploding right now. Mainly, we'll get to that soon, but just recently Kaggle released these Kaggle simulations, which are competitions of bots. So this was only a week or two ago. They released Connect 4. So right now you can go and create a bot for Connect 4 and try and win a Kaggle competition. So it's fun because it's the first time we've had a major competition in reinforcement learning, or at least for everyone, not just people going to conferences. Reinforcement learning is really good at robotics, because when you're dealing with motors and things in robotics, they have inaccuracies in them. If you tell a motor to turn 15 degrees, sometimes it'll turn 14, sometimes it'll turn 16. But what reinforcement learning does is it constantly takes in a state and produces an action. So that action would be, turning right or turning left. So if your goal is to turn your robot arm to a certain degree, your reinforcement learning algorithm can keep looking at my state. Am I at that degree yet, or have I gone too far? And adjust accordingly. Obviously, you can do way more complicated things than that, but that's kind of the idea behind why it's good in robotics. And then it's super applicable to games, because games already have reward systems built into them. So we've beaten so many games in the last 3 years. While I've been in college, it's been great. We beat Dota. We beat StarCraft 2. If you guys remember OpenAI, there was AlphaGo, which beat the world Go champion. So it's been really cool the last couple of years. And hopefully we'll see more in the coming years. So how do we kind of get into reinforcement learning as someone who's never done it before. A really good starting point is this OpenAI Gym. And so it's like a gym for your bots. They can train there. And so what OpenAI Gym does is it gives you a stable, consistent interface between a bunch of different environments so that you can have one algorithm that interacts with all these environments in the same way. And so ideally, like if we have general intelligence, which is what we're trying to get going, that would mean you can have one algorithm and it does every single environment on OpenAI Gym, and the whole world. That would be awesome. We're not quite there. It takes too much compute for a lot of things. But just like one algorithm can do a lot of these different environments, especially the ones that are like kind of simplistic looking, are really well solved. I believe that is a object trying to walk over bananas, and those are yellow and black bananas, and you don't want the black bananas. That one's kind of cool because what the agent is being given is like that image, and so it has to turn to find new bananas to walk to, which is like some interesting, thing for an agent to do, turning to scan for new information. Yeah, but let's keep going on. So here's basically what OpenAI looks like at the core. You're going to have an environment. So you can see right here we have gym.make environment. And then you're going to put an action into that environment. So gym lets you take random actions here. You can see end.actionspace.sample will just give you a random action. And you can put that into your environment and get out an observation, a reward, a flag called done, which is just, is the environment done yet? So like in the game of Pong, if you get all 5 points scored, you're done. And so you can break out. And then this fourth item called info that is not used in most environments, but it's just extra info that they could give you. And then so the way most of these algorithms are made is that they can take just that information and get better over time. So what we're going to be working on, oh no, let's just real fast move that so you can see PPO. We're going to be working on this one algorithm called PPO, and it is a policy-based algorithm. Specifically, it's called proximal policy optimization. And the policy optimization in there just means it optimizes the policy. And proximal means it doesn't go too far. There were a lot of these policy optimization algorithms that came out that were all right, but when they did something really good or really bad, they would just only do that. And so they would update their weights incredibly to keep doing the things that were good to a point that they wouldn't actually make good decisions. But notable entries into PPO, history is, so when it was published, when the paper for PPO was published, they published it with a suite of robots running around. So if we go back to that earlier slide, this robot here, oh, there you go. That robot there running, he is from the initial paper. Yeah, okay. That one's from the initial paper, so he's running through a field of obstacles, and the field is randomized every time he enters it, or they enter it. So that is like the very first application of PPO. And then we've also used it, it's just easy to access in Unity. So if you go to, I'm in Unity and I want an AI, you can train a reinforcement learning one, and that will use PPO, or you can select PPO to be used. And then most notable, very recently, we had OpenAI's 5, which was a 5v5 Dota bot. And so it would control 5 different Dota characters versus another team. And there's some stats about it that's like the OpenAI 5 would beat like 99% of all of the people that it competed against. They like let it play against random Dota players, and it won 99% of the time. So really awesome, and shows you how strong PPO can get if you have enough computing power to let it run. So what we're going to be doing is not OpenAI 5. We've got a little pendulum, and we want it to swing up and stabilize upwards. So it doesn't have enough strength to push itself all the way up, so it's going to have to swing back and forth to gain momentum and then go up, but not have too much momentum that it would fall over. And once it's up there, it has to have control enough of itself to keep it straight up and down. So we're going to apply the PPO algorithm to this. Important things we need for the algorithm. We need an action network. That's cut off a little bit. And we need a value network. We'll get into why we need the value network soon. But what the action network does is it takes an observation. In the case of our swinging pole here, the observation is going to be the sine of the angle, the cosine of the angle, and then the velocity of the pole. Those are the three things that our network is going to take in. And then our network is going to output how far to accelerate the pole left or right. So if it were to, output a -1, it would accelerate it clockwise or or counterclockwise. It's not super important to us which one is which because the AI is doing all of the interacting with the environment. There's no human interjection, if that makes sense. So the interesting thing about this is that our network doesn't have to be just for one. So we're learning about PPO, which is a way to train a network. This same network could work for on another environment. This is the bipedal walking environment. So what it takes in is 8 individual pieces of information about the state of this walker, and then what it outputs is how do I move the legs so that I can get some walking motion. And the PPO will optimize that just the same as it would for our pole. Just takes a little bit longer. So how do we train it is the interesting question. What we do is we take trajectories through our environment. So we start at the very beginning. In our case, it's with our pole straight down, but in this example here, it's a Pong game. And so you can move the pole or the Pong paddle up and down, and at some point you will either win or lose the game. And so you keep playing, you play a bunch of times and get a bunch of data, and then what you can do is take the rewards you got and propagate them backwards. Not the same way you would like backprop a supervised learning algorithm, but instead I'm trying to change the probability of taking an action if, like say it doesn't end in a win, if it ends in a lose, I'm going to take the actions along that line, along that trajectory, less often. Does that make sense? That is the confusing part.
What do each of the nodes do those represent anything?
So those are all like the different states that you would reach. Yeah.
And then is there some sort of weight attached to each action?
What do you mean by weight?
Well, the point of the agent is to maximize reward.
Mm-hmm.
So it wants to achieve the highest sum possible for reward. Is at each state, this chain of events, is there some sort of heuristic or reward policy attached to it?
Yes. So I think the answer to your question is that is what our action network does. So it takes in a state or an observation and outputs an action. And so what that network holds in itself, what it holds in its weights, is what is the probability that I take this action? And that will change as your state changes, right? I think there was a question in the back.
So like you would try a bunch of scenarios and then assign weights to based on success, right?
Yes. So it is initially kind of random, like you randomize your initial weights, and so it'll make actions, and then those will result in some wins, maybe a bunch of losses, and then it will penalize itself for the losses and try and reinforce the wins, and from there it will win more of the time, and then we go back into the game and we play more, and so we get at that sort of loop. Does that make sense?
Rewards, penalties, probability, are these strictly negative 1 to 1? Is that
Not necessarily. We'll get to how the loss function works, but yeah, we'll answer that very soon. So it's because of PPO's fun loss function. I know it's dumb, but basically what you want to look at here is that there is R sub t of theta times A sub t. That is the only important part. The rest of it, that clip function, all it does is it makes it so that it doesn't go too far in one direction or the other. And the min around that is also so that it doesn't go too far in one direction or the other. Yes?
Where does the equation come from?
So the equation comes from the PPO paper that was like initially published. But we're about to go through like what each part means, if that makes sense. So the important parts are R sub t of theta and A sub t. So this is the slide about R sub t of theta. Generally, when you're reading papers, theta is your policy's parameters. So you can kind of think of those as your weights. And then R sub t is this function that they chose to do, which is a ratio between the old parameters and the new parameters. So before you make any update steps, you can imagine that this will always be 1. Does that make sense? Who doesn't it make sense for? Okay, yeah. So what they found was if I just have my optimization be I optimize A sub t, which we will get to very soon, I will make kind of big jumps, and I'll jump into a completely new territory where my old information didn't make any sense. So to bound it and to make smaller jumps, we use this so that we don't go too far away from the old policy at any point. So if R sub t, if that ratio becomes very large, then it will no longer be the min, or it will get clipped. So let me explain what A sub t is. A sub t is the advantage function, and this is where our was that move good or not comes from. So in every time step, and a time step is a time when we chose an action based on a state. So I'm my little bot, I have my little arm right here. I chose to swing it up a little bit. My advantage function would tell me, did that lead to more reward in the end, or did it lead to less reward? And so I now know the direction I want to improve my weights. So if A sub t is negative, I know that was a bad move. So I want to negatively change my weights. And this is where that clip function comes from, or comes into play. Because if it was a bad move, I don't want to take a really big bad step. And that's where that clip comes in. It's not super important, but does everyone get the idea that when we make a good move, we want to encourage our network to go that way, and when we make a bad move, we want to discourage it? Okay, that's really all that we need. The math is just for fun. When you see a hat, I believe it's an estimation. So that is an estimation of what the true advantage is. So remember that value function from the very beginning? Our advantage is calculated from the reward minus that value function. So you can think of that as kind of like a fuzzy indicator of how good you are. So whenever you play the game, you're going to collect rewards, and then you're going to be training your value function on the rewards. Like the value function will say, in state whatever, I expected this much reward, and I actually got this much reward. So now my value function can update with that. Does that make sense? Hopefully. I know it's a lot of math, but it's a cool algorithm. Does anyone have any questions right now?
So the clip function prevents too large of a gap. It's like a hard stop.
Mm-hmm.
The 1 minus epsilon, 1 plus epsilon. So 1 minus epsilon is that that's like a maximum?
Yes. So epsilon is, in the paper, it was about 0.2. It's just a small-ish number so that you can't go too far away from 1. 1 is like where this function is kind of naturally around because, if the advantage, the ratio is naturally around 1, right? Because you're either going to be slightly more or slightly less than your old policy. Does that make sense? Okay. Any other questions right now? Yes.
SubT is the ratio of the parameters which we had earlier and the new parameters that we used.
Yes. Perfect. Okay. Hopefully that makes sense to most other people. So then we also have to train this value network. So just as we're going along and we're updating our action network to reinforce the good actions, we're also just training our value network so it can output the correct value. And we're doing this just so that we can use that in our advantage function. That make sense? Cool. Then it's time for code. So, I'm just going to copy this link. Has anyone run the code so far? Have you gotten an output? Oh, nice. So we're just going to use OpenAI Gym. Normally when we do these, we take out like to-dos so that we can type them together. I felt that wasn't super necessary for this. I think instead we should treat this like, I just found this GitHub link that is how to do a PPO, and we can kind of talk through how does that help me understand PPO, if that makes sense. So I'm going to just run this all so that we can get it started, but let's go through this code. First off, I want to see what they did with their network. Is it huge? Is it small? So what would I would probably look for torch dot something and then go down until I find something interesting. There we go. Oh, I think I passed the network. Let's look for sequential. There we go. So we use an actor-critic model, which is a fancy way of saying you have one network for actions, one network for value. It's also used in DQN. They have an actor-critic model. It also has one model for actions and one model for value. And you can kind of see that this is a very, very small network. It's 3 total layers. You have an input layer, 1 hidden layer, and 1 output layer. But it is still able to give a lot of, it's still able to hold a lot of information. Like this size of a network can do bipedal walking. So that's one of the fun things in reinforcement learning, that you don't need a huge expansive network the same way you do in like image classification. And so let's look at hidden size is not given here, it's a variable, so let's look for hidden size. Here actually, we'll just look for when we call actor-critic. Hidden size here is 256, which is pretty small in comparison to big supervised learning things. So now we just have a model that goes 3, 256 to 1, and it can do all the work we need it to do. Taking count of things like learning rate. Learning rate in reinforcement learning is fun because you don't want to overstep. So it's the what PPO is trying to do is trying to make you not overstep, and then you're also on top of that choosing a learning rate to try and not overstep. But you also want it to converge in some reasonable amount of time. So it's another art of choosing your learning rate. Does anyone have any questions about the code? Yes.
Wait, this LU Is the ReLU an optimization? The activation function?
Yes, so ReLU is an activation function, and it looks like...
Why are you using it like in the middle where you're like sequential? There's a linear ReLU and then linear.
Yeah, so the way that PyTorch does its sequential model is you just kind of stack all the things on top of each other. So you can kind of think of, I have some input nodes, then I have a next layer of loads, and then on the outputs of these, I apply my ReLU, and then you have your output. So it's kind of a part of the steps. Does that make sense? Yes.
Good question. I can pause Google this, but does ReLU mean that it also adds bias to it, or do you have to add bias separately?
I don't know the answer to that.
Sounds weird.
I've-
Sounds like PyTorch. I'm
It's
using
kind of just
I think
smashes
PyTorch-
the value.
No, I mean like when you have to add the activation function separately, do you also have to add the bias separately?
I believe PyTorch adds bias, but I don't know. Check that. Anyone have any other questions? So this should be running, and you might see a cool graph down here. This has been slight stalling to get that graph to go a little higher. In this environment, when we get around to negative 190, we have solved it. But so it's learning as it's going, and it has the chance to go straight back to nothing and then go back and down. But hopefully it goes kind of generally up. The reason that we're doing this pole environment instead of something bigger like the bipedal walker is just that it takes less time. This same algorithm will take maybe 3 hours and it will get bipedal walker working. So if you have some time at home, there's a thing you can uncomment. So if you look for bipedal, you have to pip install that and uncomment some code for the environment name. But then this same bit of code will work on that environment. Yeah. So other interesting things about this particular piece of code that, like, if you were looking at it as a GitHub repository, would seem a little weird. This subproc enevs import does something super weird. If you ever see this again, what it does is it takes a bunch of OpenAI environments, so like things that have like little poles in them. It puts a bunch of them in parallel, and it lets you treat them as if they're one. So I can call .step on one of them and get all of the observations out, and then I can give it all the actions again. And so it lets me use it as one, even though I'm doing 16 at once, and so I get more information for my time. Yes?
Wouldn't that give you just 16 duplicate data points?
Yes and no. If there were no exploration in this algorithm, that would be true. But I didn't explain this, but when PPO selects an action, it doesn't give you a precise number. It actually gets you a distribution. So if we go to, I know that sounds scary, but it's not. It's cool. If you look for normal, you'll see that when you call the forward, so in PyTorch, forward is what you do when you call the model. So you give it an observation, which will be x, and then that will run it through both value, or both through the actor and critic, and then you can see what it does with the output of the actor. It doesn't directly give it out back to the environment. Instead, it puts it into a normal function, and you get a distribution out. And then when you want to get an action from it, you sample from that distribution. So this means that we kind of get random actions centered around what we believe is correct. And then we update what our mean is, and we keep doing that until we find the correct mean. Some people, when they're doing this, they start with a very large standard deviation to get a big normal function, and then hone it in as they're increasing their number of steps. Other questions? Yes.
Is that kind of like how they get the approximate part?
What?
Like, so you said it's like not as, they use approximate because it's kind of, doesn't give you the best policy always, it kind of gives you like a range of it, right?
Mm-hmm.
Or is that why they're kind of using the distribution for that?
Or is that something completely different?
Wait, what do you mean by they don't always give you? When I was saying that they don't always give you the best approximation, I was talking about the value function.
Gotcha.
But it is similar.
Gotcha.
Yeah. Does anyone? Okay. Then we see how this is going. Oh wow, that's really close. Oh, actually, I think it did do it. Okay, and then really unfortunately in Google Colab, you cannot show matplotlib like images super easily. So I wanted to show a video of it working. So it requires this entire block of code where I import a bunch of stuff. It's terrible. But down here, we get a nice GIF of it working. And so you'll see every once in a while it resets, but it swings up and keeps itself upright. And that is the main, how does it work? More questions. I'm sure there's tons. Yes?
Where does the loss function get used in this code?
So if you go to PPO update, you'll see range of PPO update or epochs. What this PPO iter function is doing is basically just randomizing it and putting it into small mini batches. And then we make the loss function here. A lot of the reasons, or a lot of the things that are weird about this code is that you have to keep track of a lot of things. So you have to keep track of every return you got, every observation, and then they're all used at once in the loss function. So this is where it is calculated. If you have specific questions, I can answer those. Let's see. Let's see. What else? You can see our epsilon, the clip param is used here, and surprisingly, Torch has a clamp function, so it works exactly the same as the paper. Okay. Yes.
What do the actor loss and critic loss, how are they, what does it mean?
Okay. So your actor loss is how far away you are from taking the correct actions. So that's the actor is what makes actions, and then the critic loss is how far are you away from correctly predicting the reward you were going to get. So that the critic is that value function, and the actor is the action network. Does that make sense? You remember those from the previous slides? Okay. And then Torch is really cool because you can make one loss function at the end and then backwards on it, and you only have to call backwards once, and it will go back through this line here, and it will assign the correct it will assign correctly who did what so that the gradients are propagated correctly. Worst named variable. Return underscore. So it was something called returns, and I wanted an individual piece of it. This isn't from my code, but I hate it. So it is, I was iterating over something called returns, and so what is an individual return? It would be a return, but you can't write that, so they just put an underscore. Yes?
What does SURR mean?
SUR, so these are two, they're like surrogate, I believe. They're surrogate losses. That could be wrong.
What was the Git last week? Where did you find this?
So this is pulled together from a couple different things, a lot of Medium articles, but I can link you the Medium articles and GitHubs that I found from.
Did everybody get it working?
It should just, yes.
Yeah. I
Yeah.
know this is really complicated. Then
Yeah. I think, yeah. There's got to be a way to explain this better.
reinforcement in 175, right? Where you're taking 175,
Yes.
you do a ton of this stuff.
So an interesting thing about how this is currently set up, it will work for continuous environments, which are things that like have motors in them or like use kind of force, whereas some environments have like actions. And the way you would change this from continuous to actions is just have a threshold. So like instead of treating my integer as a mean, and that mean is the standard deviation of my force, instead it would be, it's a probability. I would maybe put like a sigmoid on the outside so that it goes between 0 and 1, and then I can threshold it at 0.5. And so what my reinforced algorithm would do is push it below 0.5 or above 0.5 to select that button on or off. Yes. Oh no, you were just stretching. Yes.
Wait, so last week we learned about the recurrent neural network, and then before we learned supervised training, and then this time we learned reinforcement. Like, when do you know which one to choose from? Like,
So that depends a lot on your problem. So like supervised learning, if you have labeled data, you're going to use supervised learning. So like if I have a bunch of pictures of cats and dogs and I know, and I have labels that they're cats and dogs, that's generally supervised learning. If I have an environment that I can play with, but I don't know optimal play in it, that's reinforcement learning. If I have a bunch of data that's just kind of, I don't understand it, but I want to know the underneath structure of it, that is unsupervised learning. And those are kind of the three pillars of like the current stuff that we're working on.
so like reinforcement is like kind of exploring around?
Yeah, it's like super optimization. So like I have an environment, I want to optimize that environment. Yes.
Did you just do this for fun?
Yeah, a little bit. I had a class. There's 172B, and in that class you have to make an AI, and it has to be good enough for this teacher. And so our idea was we'll make a robot arm that tries and picks something up. And so I learned as much of reinforcement learning as I could so that I could get that robot arm to work. In the end, I didn't, but I got real close.
Is taught in this room.
Really? Are you guys, is 175 still Minecraft?
You can choose Minecraft, Ducky Town, which is like self-driving robots.
Oh,
And
nice.
The last one is called CMRL.
CMRL.
It's
Okay.
a multi-agent stuff.
Oh, okay.
I think it was developed at UCI actually.
Mm-hmm. In like the Baldy lab?
Not sure. I didn't look into it too much.
Okay. Yeah, I know there was someone working on that. But if you do cars have continuous motors, so that would be a use of this algorithm. You could use this pretty much plug and play.
In the case of StarCraft 2, Dota, those sorts of games, were they using strictly reinforcement learning? They were multi-agent models, right?
Yeah.
They're not necessarily using off-the-shelf models. How do you think that they customized their models by using StarCraft?
So they're the ones at the forefront of all this. So they made the models that are off-the-shelf models. So they're using their own stuff. In the case of StarCraft, I know they had multiple networks. They had like a network that would choose what part of the map to look at, and then another network that would choose like buildings to select. And so they did a couple networks to make one bigger AI.
So they're combining neural networks. Are they using different techniques for each of those neural networks?
I believe they're all using reinforcement learning. Like, if I lose, do something. But yeah, so they're all using reinforcement learning, but they might be using different network architectures and like different ways to train them.
Like you read about some AI with like Atari, for example.
Yes.
Classic domain.
Mhm.
Like, they don't give them rewards or something, policies, and they're expected to just explore the environment. I think I saw one of those videos, like 2-minute papers. He was talking about an AI that could play Pong or Doom or something like that. Except that they're not given, it's totally unsupervised, and they're not given any heuristics. And so they have to learn how to explore the environment on their own. And I think That's pretty cutting edge. I don't know how to do that.
I think I know which paper you're talking about, and it's they give them a reward, but the reward is just how badly can you predict the next frame. So it leads to exploration. So the only way, so like we're good at supervised learning. If I've seen a frame before, I can train my neural network so that it can predict it again. But if it's entered a new area, it's not going to be able to predict that next frame. So that's when it's rewarded. So it's like it's the exploration learning, right? Yeah. So it is rewarded when it reaches an area it can't predict.
I wonder, Subproc is such a complicated game that they were left with a lot of skepticism as to whether it could be
Mm-hmm.
I think they've laid the critics to rest, but part of the skepticism is that you have limited field of view, you have complex resource management, and so many actions that have to take place, different gameplay strategies. I wonder, because they're not just managing like very specific tasks like training units to attack them. They have to do resource management, exploration of a field that's deliberately committed by these design makers. So I wonder how they encourage the AI to explore,
Mm-hmm.
how they encourage it to do basic defense or offensive strategies, things like that.
Yeah, I think that's all about like how reinforcement learning works. Like you want to figure out how to make it explore while still exploiting things that it's seen. And so they're leading this stuff, so they're very good at it. Yes, I think if there's no other questions, I think that this is good for this meeting. You can do whatever you want now.